Hi there, my name is Charles Welsfan Msipa. Welcome to Edlangezwi presentation of mathematics. Our topic today is mathematical induction. This presentation I would like to apprentice you in doing what is called proof by applying the principle of mathematical induction. So let's open this way. The business of mathematics is about discovery and the proof, and the rest is learning to use the proved discoveries in the human activities. You can entertain yourself with that statement. I hope you enjoy it. Now, turning to induction. Induction is about properties of natural numbers. I hope you remember that natural numbers are represented by this symbol, and that's the set of numbers that starts from 1, 2, 3, and so on. And you also need to know, by now you should have learned a lot of things about natural numbers, especially also how to represent maybe subsets of natural numbers. For example, you take natural numbers 2n to represent even numbers, and you can also take this 2n minus 1 to represent what you call odd numbers. So all this is assumed knowledge. I hope you understand what are even numbers. Simple, these are numbers which are divided by 2, and these are numbers which when you divide by 2, you have got a remainder of 1. So because when we state some properties of natural numbers, we may speak in terms of even numbers or in terms of odd numbers. So now, to learn how to prove or proofs applying the principle of induction, let's start first of all by looking at the following. Now, what we have here, we have natural numbers, and what you see in the first line there is stated that 1 is a perfect square, which is 1 squared, and then in the next row we've got that 1 plus 3 is equals to 4, which is a perfect square, so 2 squared. So if you check what we're talking about here, 1 and 3 are what we would refer to as odd numbers, now as odd natural numbers. And then coming to this next row, we've got 1 plus 3 plus 5 is equal to 3 squared. So which are again a perfect square. So what we can do when we do some kind of maybe curious investigation about numbers or just some experiment about numbers, we can observe or discover some kind of a pattern or some kind of a effect or something which we don't really know whether is true for all natural numbers, which sometimes mathematics you can say we can conjecture. We can have a conjecture about natural numbers, and then mathematics does not end there. We need to take that to a logical proof of whatever we've conjectured. Now, the principle of mathematical induction is some kind of a theorem, which maybe let's look at it this way. It's stated this way. Principle of mathematical induction, it says for each natural number n, if a statement about natural numbers, in this case for a statement we write that as Pn, a statement about natural numbers is made, and we suppose that the following two are true. Now it's true for the first natural number, which is 1, and we can also show that if for every natural number k is true, then it's also true for k plus 1. Then we can conclude that this is true for all natural numbers n. That's what the principle of mathematical induction says. Now, what is important now is to learn how to, when we've got a statement or a statement about natural numbers, let's say a statement Pn, this Pn here denotes a statement which is said about natural numbers. In other words, in the previous slide there, what you can say is that the sum of 1, 2 odd numbers is equal to 2 squared, and then the sum of 1, 2, 3 first odd numbers is equal to 3 squared. So we can end up having a statement which is about natural numbers, in this case natural numbers which are odd numbers. So now what is said here now, if you can show that is true for the first natural number and show that is true, if it's true for k, is also true for k plus 1, then you can conclude that that is true for all natural numbers. So now let's look at the very first pattern and try to see if we can prove it using this principle. He said here, prove using mathematical induction that for all natural numbers the following statement is true. What is the statement? That the sum of n odd numbers is equal to n squared. So now I'll explain the proof of natural numbers by doing it. So when you're going to prove a statement using natural numbers, the initial step, which I've labeled here as 0, is to do a test for the first number. In this case, you are going to do a test for, in other words, you test the statement for 1, which is the first natural number. Now, that's what we saw before, that 1, the sum of 1 alone is equal to 1, and this is equals to a perfect square 1 squared. So we've already seen that it happens also for 2. Now, in the next step, what we do, we are supposed to test if, let's say, this is true for k. Now we make an assumption. That is true for k. Then we need to show that it is also true for k plus 1. In other words, if we assume that is true for k, what we'll be saying is 1 plus 3 plus 5 plus up to plus 2k minus 1, which is an odd number. This will be equals to k squared. So if we assume that this is true, this becomes what we call our induction hypothesis. So now we need to prove that is true for k plus 1. So I'll write here k plus 1 and put a question mark to sort of as a question whether is it true for k plus 1. Now how does this look like for k plus 1? This statement will be written as 1 plus 3 plus 5 plus dash 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 plus 2k minus 1 plus 2k plus 1 minus 1. This will be equals to k plus 1 all squared. Let's note what's happening here. You see, in this part, we went up to 2k minus 1. So the next number after this one would be 2 times k plus 1, and then since we know that it's an odd number, we write it as 2k plus 1 minus 1, and then this should be equals to k plus 1 squared. So now we'll actually use this hypothesis to show that this is true. So now proceeding, what would happen here? What we have up to this point is what we assumed, that this is k plus 1. So applying that, you can say this is k squared plus 2k plus 1 minus 1. We need to work with this left hand side to deduce that this is equals to k plus 1 squared. So let's proceed this way. What we have here, we have k squared plus 2k plus 2 minus 1. So note that I've just removed the brackets here, and then we get this way, and then we proceed here by saying simplifying this. What we have here, we can see that this, I'll write here this, that is equal to that, and that is equal to k squared plus 2 is 2k plus 1. Actually, at this point, I think let's label this as our left hand side being equal to that. So we're simplifying our left hand side here. Now, having simplified this left hand side, I think we can see that we've got something familiar here, which is a quadratic expression, which is we can factorize, and we can see that this is actually a perfect square, which is k plus 1 all squared. If you're not sure that, you can double check that, but this is a perfect square. Now what we've got here is our left hand side, which means that this sum, with our assumption that our hypothesis that this is equal to k squared, actually simplifies to k plus 1 squared, and this is actually our right hand side. So what we've just shown here is that this statement, which we assumed that is true for k, we have also shown that it is true for k plus 1. So after this first step, initial step of testing our hypothesis and deducing from our hypothesis that is true, our hypothesis is about k, and deducing that is true for k plus 1, we can now have a conclusion, which will be our last step, because everything we do, we must at the end state what is our conclusion from what we have done. So according to the principle of mathematical induction, we've shown that the initial step is true, and we've shown that if it's true for k, it's true for k plus 1. So according to that principle of induction, we can now conclude that this is true for all n a natural number. So I hope maybe to some of you, this is the first proof of induction, or some of you have seen it before. I hope this explanation enriches on what you already know. And what's going to follow, we're going to take further examples on this and try to prove using the same principle of mathematical induction. And on your side, you should also try to practice with different examples which you get from your text or from other sources. Otherwise, for now, I would like to say thank you for listening.